Hello everyone. Today we will be talking about the generative models, and we'll look at what is the objective of the GAN, how we optimize it, followed by variational autoencoder, and then its implementation in PyTorch. So far, the models we have seen are discriminative in nature. What I mean by discriminative is that suppose if we are given a training data, which is x1, y1, x2, y2, and so on. This is a label training data here. What is actually the model learning? So the model is learning to predict the label of the input during testing. So suppose at next time during inference we give x test as an input to the model, then the model is tasked to predict the most likely label for this input. This is an example of discriminative model where the goal of the model is to learn some kind of hyperplane in some high dimensional space which can separate the inputs into different classes. Here, in case of discriminative models, we are not focusing on the distribution of the inputs itself, but looking at the probability of y given an input x. However, when we talk about generative models, this is different from discriminative model. In generative model, we directly try to model the underlying data distribution P of x. So suppose D represents the training data, which is the samples drawn from some underlying data distribution P of x. Then here the goal is to learn this underlying data distribution itself so that we can sample multiple inputs from this data, which is very similar, to the training data itself, right? So here the objective here is not modeling P of y given x, but directly learning P of x. So, and how to learn P of x? We try to have a parameterized model for this, where the parameters are represented by the theta, and we aim to find the theta which can minimize the distance between two distributions. The two distributions here are the true data distribution, which is unknown to us, and the parameterized density model, which we are trying to which we will be using to approximate the underlying data distribution. Here we do not know P of t, but we do have the samples drawn from P of t as x1, x2, xn, which are available to us during training phase. We are trying to model the underlying data distribution P of x, which is parameterized by this theta, and the goal is to find the theta which can approximate the underlying data distribution as closely as possible. So since we just talked about this generative and discriminative model, here's a simple question that in generative modeling, we generally try to minimize the distance between two distributions. The two distributions are the true distribution and the distribution we are learning, right? So how to minimize the distance between two distributions? For this, we used some metrics like KL divergence or JS divergence, and so on. So these are the metrics which are mainly used to minimize or measure the distance between two different distributions. So as I said earlier, in generative modeling, the goal is to find the theta which can minimize the distance between the true and the learned distribution. So for that, we try to minimize the KL divergence between these two distributions. The higher the KL divergence, the more different are these two distributions. The lower the KL divergence is, the closer these two distributions are. So the aim here is to minimize the KL divergence between the unknown true distribution B and approximating distribution Q of theta. The problem of learning a true distribution then simplifies to quantum. So these are certain options and we have to find the right thing. So let's look at mathematically what it means. So the aim is to find the theta which minimizes the KL divergence between the true distribution P of t and the approximated true distribution P of theta, which is parameterized by this theta. So this expectation is computed, its divergence is computed as expectation over x drawn from this P of P, which is, so we do not know the underlying distribution P of T, so then we will look at the training data which is available to us. So the expectation of log of P of T given P of theta, just give me a minute, I'll let people join the meeting. So here, yes. So now we try to minimize the KL divergence between P of T and P of theta. And that is done as minimizing the, so what is the KL divergence? KL divergence is nothing but expectation of log of P of T given P of theta over this X. And since we do not know P of theta, so we are taking the X sample from the training data, right? And that becomes expectation over X drawn from data. There is also one P of T X here. So there is a typo. So it will be expectation over X drawn from data, and this will be P of X log of PD of X by P of theta of X. Okay. And now because we are talking about this data which is available to us, it will become as, because we are trying to optimize with respect to theta, this PD becomes a constant, and this will reduce to expectation of minus expectation of p theta of x, and this will be pd log pd of x, but this will be constant for us, right? So we can ignore this term and can just focus on this term, and this term is nothing but minimizing the negative log likelihood of the uh, approximative distribution, okay, with respect to theta. Okay. So minimizing negative log likelihood, which is same as maximizing the log likelihood, and therefore identifying parameter theta by minimizing the KL divergence is equivalent to finding the parameters theta by maximizing the likelihood estimation of this training data, which we have seen. Now, the second question is that given an input x and output y, which of the following is the quality of quantity of interest in discriminative modeling? So as I said before, that in case of discriminative modeling, the aim is to predict the label of the input given the input. So we just look at P of y given x. We are not trying to model P of x here, but just looking at y. Then generative adversarial network. So we saw what generative network tries to do. And now we will look at one of the very famous and commonly used type of network known as generative adversarial networks. The aim here is to generate the images which is drawn from the same. So basically, you're trying to generate images which are very similar to the images we have seen during training phase. Okay. But at the same time, they are also different. So we are not just generating the exactly same image, but we are generating the similar images. So here is a very simple comic example of what GANs do. So in GAN, suppose there is a bank, and the bank is printing this money, which is the real currency. And then there is also gambler. 1 minute. Hi. So I think we are here. So I'll repeat what I'm saying here. So it's generative adversarial networks. We are talking about generative adversarial networks. This is a type of generative models which try to learn the underlying distribution. And how we do that? So for that, we generally try to, let me go back. So for that, what we do is basically try to approximate the underlying true distribution P of t with P of theta, and theta being the parameters we are trying to learn. Okay. So once such model is this generative adversarial network, here is a simple example of what this can look like. So here is a bank, which is tasked to print the real currency. And then there is this fraud person, which is also printing the currency, but this currency is not the real currency. And there is this cop, which can make a distinction between the real money and the fake money. So in this process, if this fake money is significantly different from this real money, then this person will be easily arrested because he is using this money, right? And in other way, and this discriminator is tasked actually to distinguish the real money from the fake money. So overall, we want the generator to generate the money which is very much similar to the real money, so that it is difficult for the discriminator here, the cop, to distinguish between the real and the fake money. At the same time, for the discriminator, the cop, we want it to be smart enough to distinguish between the real and fake money, irrespective of how good or how realistic is the fake money. So this is like a min-max game, right? Because we have to maximize the performance of the discriminator, we have to maximize the performance of the generator, whereas the generator is trying to fool the discriminator, right? So fooling the discriminator is like lowering its performance. So you can see it that way. So here is a block diagram of what GANs are. Suppose we have two models here. The generator model representing this fraud person here, the discriminator representing the cop, and so these are the fake images which are being generated by the generator. So this set represents the latent space embedding, which can be seen as a noise. We will come to this later, and we can feed this noise vector to the generator and expect it to produce an image which ideally should be very similar to the real image. At the same time, to the discriminator is tasked to distinguish between the fake images and the real images. So the discriminator is a classifier here with only two outputs. If it is real, the output should be 1. If it is fake, the output should be 0. Okay. So here, the training objective is, let's try to understand it first for discriminator, and then we will go to generative. So for discriminator, we want discriminator to be good. So definitely we want that on real images. So this first term is representing the real images here. So expectation over X drawn from P of data over the images drawn from the real data or from the training data. This discriminator should be able to classify them as real, right? So for that, it should maximize the probability of it, and d of x is representing the probability here. So log of d of x should be maximum. Okay. At the same time, for the inputs which are generated by the generator here, d of z is representing the distribution length of the generator. So the inputs generated by the generator, we expect the discriminator to be fooled. So it should print them as, it should label them as fake, which means we want to maximize the probability of class fake, which is similar as minimizing the probability of class real. So that's why we have 1 minus d of g of zz. Okay, so g of z generator is representing g here. So g of this z, which is a noise variable, a vector we feed it into the generator, is representing the input generated by the generator g for the input z. And how does now, and what is the goal of the generator in this thing? So generator is trying to fool the discriminator, right? So what it is trying to say that in case of generator, it wants the discriminator to predict these generated inputs as the real inputs, right? So for that, what will happen is that this generator will make sure that this value is being minimized. So that's why it's a min-max game. So the discriminator is trying to maximize it while the generator is trying to minimize it. So the reward for generator, which is basically the discriminator was able to classify the fake image as real image, is actually a negative reward for discriminator because discriminator fooled classified images. Now, so this is the actual loss of the divergence which has been tried to minimize in case of GANs, which is this J's divergence between the underlying data distribution, which we don't know, P of data, and the distribution which this generator is learning, represented by P of G. And this is nothing but half of KL of PB, the KL divergence between the PD, that is the underlying data distribution, and P of G, which is the distribution learned by the generator, plus KL divergence of P of G and P of D. Note that we are not aware of what P of D is, but we do have samples from P of D as our training data, and we will be using those samples to compute this KL divergence here. Now, this is the training part. During inference time, we don't need the discriminator. We are interested in generating the images, and that can be done only using the generator model. So, a Z, which is this noise, will be fed to the generator, and it will give us an image, which should be, once the model has been converged, which will be very similar to what real images look like. Quite realistic images. The other generative model, which is very popular, is this variational autoencoders. It is slightly similar to autoencoders, but in case of autoencoder, the goal was to map the input to some hidden latent space from which we can reconstruct the input. So it could be seen as mapping a high dimensional data to some low dimensional data without losing much information. That was the aim of autoencoder. In case of variational autoencoder, we are not only interested in mapping those embeddings, because eventually it will happen, but we are interested mainly in generating more samples from that latent space. We are finally, so we are also interested in generating more samples from the underlying data distribution. The architecture, however, will be very similar to what we have for autoencoders. We will have an encoder component and a decoder component, similar to autoencoder decoder. And we will have this X, which is our training data, sampled from the true data distribution. These inputs will be fed to the encoder. Now, in case of autoencoder, the output of the encoder was Z, which was the latent feature representation of the input X. Here, since we are trying to generate the samples, we will link each input with a latent variable Z. Okay, and this encoder will now try to model this distribution, which is Z given X. That is, given an input X, what should be the Z? The distribution over these latent variables Z. Okay, and this distribution, for this distribution, it assumes it to be a Gaussian, and therefore a Gaussian since a Gaussian distribution can be represented well using the mean vector and the covariance matrix, the encoder will predict the mean and the covariance of this distribution, which is the distribution of Z given X approximated as Gaussian. Okay. Once we know the distribution of the latent space given the input X, we can then try to sample inputs from this distribution and get outputs which are very similar to the inputs itself X. Okay. So, given this Q of phi of Z given X, we will try to sample certain Z. So, we sample a Z from this Gaussian, and the parameters of the Gaussians are being predicted by the encoder here. So, there is mu and sigma. Okay. Once we have this, we will give it as an input to the decoder, which will try to model P of theta of X given Z. So, decoder can be seen as the module which is modulating the component of P of X given Z now, and it will finally give the output X, and that output X hat should be very close to the input X, because we used the distribution of z given x, right? So we actually have a distribution of the latent space given this input x, and sampling from that distribution should give us an output which should be very similar to the input x itself. Okay, if we sample close to x in that distribution. And the final loss function for variational autoencoder is simple: x hat minus x, the L2 norm of it. Okay, in GANs it was min max. Here we just have a reconstruction loss between the generated image and the true image. Okay, now this can be seen as maximizing the evidence lower bound. I'll go 1 minute. So now, hi Shubhangi, we are talking about variational autoencoders, and this, yeah, hi. So in case of variational autoencoders, this is very similar to autoencoder, but with the aim of generating the images. Okay. In case of autoencoders, the aim was to map the high dimensional data to some low dimensional data without losing much information, from which we can reconstruct the images. The similar concept is being followed here, but now the goal is also to learn the distribution z given x, and then to sample images which should be similar to x but may not be exactly same. Okay? And then this can be seen as a generative model. The loss function which we use for variational autoencoders is the L2 norm between the true image and the generated image, and this can be seen as maximizing the evidence lower bound to learn the encoder and decoder parameters. And here the parameters of the encoder are represented by phi, and the parameters of decoder are represented by theta. Here by parameters I mean the weights and biases of these modules. Okay. The other loss function which is very common these days is, other than this reconstruction loss, we have also a loss on this latent prior. So when we learn this distribution of z given x, we assume the prior over z was a Gaussian, standard Gaussian with zero mean and identity covariance matrix, and now we want this posterior of z. This is known as posterior of z. So we want the posterior of z should be very similar to the prior, and thus we try to minimize the KL divergence here. This term act as a regularizer on Q of z kinetics as well. Okay. So this P of C is like a regularizer for this loss, for the learned distribution, and trying to make Q z given x match the P of z. So that is what the KL divergence do. KL divergence try to minimize. When you try to minimize the KL divergence, the goal is, the aim is to minimize the distance between two distributions. Okay. So here is some interesting questions we can look at. Okay, this is basically that we talked about this GANs here, generative adversarial networks, and it, yeah, yes. Oh, okay, okay. I'll. Is it visible now? Okay, okay. Oh, I'm so sorry. Maybe it got disconnected. So basically, I was talking about this variational autoencoders, and which is one of the generative methods, and in which we have this encoder and a decoder. We give a true data here for training data and predict this the mean and the covariance of a distribution, which is representing this q phi z given x. Okay, and phi are the parameters of the encoder module, and then using these predicted parameters, we sample an input set again and feed it to the decoder, and then decoder will try to construct the x hat. Okay, and that x hat should be And to train this model, we will have a simple reconstruction loss between the x set and x. Okay. Also, in the later versions of Variational Autoencoders, we also had a clear divergence loss between this q z given x and p of z. So what is q z given x? Q z given x is the posterior distribution of the latent variable z given the input x, and p of z is the initial prior over this latent variable z. Okay, so we try to minimize the clear divergence between the posterior of z and the prior, and here the prior will act as a regularizer here. So the goal is that predictive distribution should still be very close to our prior distribution, which is a standard Gaussian. Okay. Now here are certain questions with respect to autoencoders and GAN, and we'll try to look at it. So the first question here is that okay, one thing I think that was being covered in the lecture slides already. I'll just repeat it. So when we talk about GANs, like especially this DC GAN, the leading embeddings which we learn, okay, that we can do some kind of arithmetic operations on those latent embeddings and can get some results we like. Okay, so for example, here if you look at this question 6, if you are given the average of the latent vectors corresponding to men with head V1, men without head V2, and women with glasses V3, which of the following is the most probable generated images with the latent vector V1, V2, V1 minus V2 plus V3? So now V1 is representing two attributes, which is men and head. Okay. V2, roughly speaking, so V2 is representing the attribute of man only and no head. So if we do V1 minus V2, it should give the attribute head. Okay. And then we add the latent embeddings of V3, and V3 is representing women with glasses. Okay. So finally, after this evaluation of this arithmetic expression here, we get women with glasses and head. So this should possibly help us in generating the images women with head and glasses. Okay. The next question I want to discuss is, in case of VAE, the encoder outputs mu and sigma. Okay, so this mu and sigma is what this encoder is outputting here. So we now have the value of mu and sigma, and there is this epsilon which we have sampled from a standard Gaussian. Okay, and the sampled value of the epsilon is this. Okay, here we are talking about a three-dimensional Gaussian. Okay, so the mean vector will be of dimension 3 and the covariance matrix will be of dimension 3 cross 3, but we are talking it as a diagonal covariance matrix. Okay, so it's a diagonal matrix with only these as the diagonal entries. Okay, then the latent value set given to the decoders. So remember this diagram here. Once we have the output mu and z, mu and sigma from the encoder, we use it to sample z, right? But in this example, we have sampled it from a standard Gaussian of 0, I. So how can we sample it from this distribution? The idea is, here we will try to do this. So this is z is equal to mu plus sigma times of epsilon will now be similar to sampling z from the Gaussian with mean mu and sigma. So after doing this computation, we will get the value of the latent variable z, which will be sampled. Okay. This is an quite a question we see. So which is, when can GANs and VAE fix? So VAEs are basically trying using this maximum likelihood criteria. So if we are using this maximum likelihood criteria, then VAEs will try to fit. Okay. And in case of GANs, suppose, so this is the blue distribution here, which is a true distribution, and it has two modes. One mode is this, and the other mode is this. Okay. Now the issue with GAN is that it is able to not model both the modes. It will try to stick to one of the modes. So GAN may fit to exactly one mode here and ignore this. So this is the issue with the GAN, and that is known as mode collapse. However, recently there have been a couple of papers which try to tackle this issue, and there we have seen that the learned model is able to generate images not only from this mode but also from the other neighboring areas. And in case of VAE, it will be overfit due to this maximum likelihood criteria and may not be able to model the actual true posterior distribution. Okay. Now, I would like to discuss the implementation of variational autoencoders in PyTorch. So, do you have any questions so far? Okay. So we'll look at this then. Autoencoders. So remember, in case of autoencoders, we had this kind of architecture that if X is there as an input, we used to get a latent space embedding of the input X represented by Z, which is then fed to this decoder network, which reconstructs the original image X set. So it was a way of mapping high dimensional data to some low dimensional data, but without much loss of the information. So first, let's look at the implementation of the autoencoder decoder, and then we will look at the implementation of the variational autoencoder. So for encoder decoder model, we need two components. One is encoder, the second component is decoder. Whatever the input will come, we will feed it first to the encoder to get the Z. Once we have the Z, we will feed it to the decoder and we will get the X set. Now, let's look at the module encoder. So encoder here has been coded as class encoder, and it is a two-layer fully connected network. So basically the input dimensionality is 784. We are talking about MS data set for right now. So the images are 28 cross 28, resulting in a 784 dimensional vector. So the input is 784 with the hidden dimensions factor. And then we have another linear layer, which is connecting this 512 dimension output to some latent dimensional output. Okay? And this latent dimension is the size of the vector Z. So this Z, okay. So the size of this Z is this latent dimension. Okay, and we can parameterize this. So we can try different sizes of this dimensionality. And how to forward an input to the encoder? Flatten the input, convert it into a single one-dimensional array, pass it to the linear layer 1, apply the random activation, pass it to the linear layer 2. Then the decoder is implemented as another class decoder, and it is also a two-layer network, similar architecture, mapping latent dimension to 512, 512 to 784. Same way again, whatever is coming, pass it through the first layer, apply the random, pass it to the second layer, apply the sigmoid. Why we are applying the sigmoid? Because sigmoid gives you an output between 0 and 1. These are images, tensors, which is in the range of, originally maps in the range of 0 to 1. So just to do that, we have applied the sigmoid. In case you are applying the transformations like normalizations and all, then the image may not be in the range of 0 to 1. So there you can try to remove the sigmoid. Okay, once we have this encoder decoder, we will, so this is how we have created the autoencoder, and now training the autoencoder is simple. So for that, what we need is we need data. Okay, we need this data. Once we have the data, we need an optimizer. So here the optimizer is added, and we are optimizing all the parameters of the autoencoder. And the parameters here are the weight and biases of each and every layer in encoder and decoder. Then training the model for epochs, number of epochs. For each X and Y in data, we are not interested in Y. Y is the label of the image. So we can ignore Y for now and just focus on X. So converting this X to the device, if it is on GPU, the model is on GPU, then move the image X to GPU. If it is on CPU, the model is on CPU, then there is no need. Then passing this input X to the autoencoder, getting the X head, the reconstructed image, applying the reconstruction laws, x minus x hat, the LT norm of it, and backpropagating laws, and not optimize that. So we have all the training in, like we have all the ingredients necessary for training. We have the training module ready, we have the model ready. The only thing left is the data part. So here the data is nothing but this MS data, which has already provided in the data sets. Just loaded it. Transforms, here we have applied nothing but just have converted it to tensor. So here the range will always be between 0 to 1, and that's why we had used sigmoid in the decoder. And the backside of 128 is used. Shuffle is important because we are iterating over the same data set multiple number of times. So adding shuffle will definitely add this to plasticity to the model, which is good for generalization. And then passing this data, training the model. So for training the model, we pass the autoencoder and data as an argument to the function train. Here is the output. The model has been trained, and let's try to plot the relative space. So in this data, we get the relative space embedding of different images X, and then try to plot it according to their classes. So this is the plot you can see here. Okay, remember here we do not have to do any dimensionality reduction. The reason is we have already used the latent dimension as 2. Okay, so Z is already 2-dimensional and therefore it is easy to visualize. In case the Z is very high dimensional, then you might need to use other dimensionality reduction algorithms like PCA or TSNA. So plotting these Z1, Z2 according to their class. Here each color represents their class label. So here this represents their class label, and then you can see that this orange is representing 1 and the embeddings of 1 are somewhat close here. The embeddings of 9 is separate from 1. The embeddings of 7 is closer to 1, which we can expect something, and so on. Okay. Sorry, this is the embedding of 0. 9 is also closer to 7. You can expect, right? 7 and then 9. So this is how the autoencoder embeddings are plotted. Now, if we try to see the reconstructed images, okay, so this is autoencoder. Okay, so basically we give X as an input to the image. What we're trying to do here is, okay, so suppose we try to generate the reconstructed images. Okay, so image is a 0 image. Okay, this is a 0 answer here, and we take this LP dot space, that is number of images we are trying to generate here is 12. And then we try to give them as an embedding to the autoencoder and try to get the Excel. So if we have something like this, a random vector set, and we give it to X head, then what will be the output? Okay, and then we try to visualize it here. So this is how this plot reconstructed autoencoder looks like. So you can see that the images of 7, and as we are changing the vector set, it's getting printed towards 8 and so on. Now, but you can see that it's not very clear, right? It's not showing any transition as such much. We can do better, and for that comes the variational autoencoders, which says that given an input X, the encoder will now predict the parameters of the distribution mu and sigma. This is sigma of X. Okay, mu X and sigma X, and then from this distribution, we will try to sample Z, which is represented by this green, and we'll give it as an input to the decoder that will predict this X head, which is the reconstructed image and should be very similar to X. Okay, so implementing variational encoder and decoder, and then we will try to train this model and look at its output. Okay. So in case of variational encoder is a two-layer network again. So we map from 784 to 512. The first layer is same. However, in second layer, instead of having a dimensionality is 512 cross latent dimensions, which we had there, we have two layers, linear 2 and linear 3. The linear 2 is responsible to predict the mean, and the linear 3 is predicting the variance. Okay, and once we have this mu and sigma, we also try to find the clear divergence. Okay, so remember, in case of autoencoders, we just have reconstructed loss, but in case of variational encoder, we have this reconstructed loss plus clear divergence loss. So that clear divergence loss is being implemented here. Cell.kl is 0. Okay, and this n is basically trying to get the nothing but the normal distribution from which we will be sampling the z. Okay. So for the variation encoder, it's very easy. Get the input, flatten it, pass it through linear 1 layer, then get the mu and sigma. Then sample a z from this mu and sigma, which is similar to mu plus sigma, into a sample drawn from a standard Gaussian. This is representing our standard Gaussian. Okay. So sample an input from this and do this. So this, remember that mu plus sigma epsilon, so the same expression we are doing here. We get the set, and at the same time we are also computing the clear divergence between this distribution sigma and mu which we got here and the Gaussian distribution, which is a normal standard Gaussian here. Okay, and computing this is our clear loss. In case of variational autoencoder, what will happen is we also needed, so this was encoder module, right? But we do need a decoder. However, we can use the same decoder as we did before. Okay, so for this, the decoder is the same as the decoder we use for autoencoder. There is only a change in case of variational encoder because this is different, and that we have implemented. So now, following the same procedure, we train this autoencoder with this variational encoder module and the same decoder module. Okay, and once we have trained, we try to plot its embedding, and you can see here that these embeddings are better separated as in comparison to the autoencoder embeddings. Okay, for example, this is 1 here, this is 9 here, but there are also certain examples of 9 which are very far from 1. At the same time, we have 0, which is again separated by a large margin from 1, and so on. The next thing is that we would try to visualize how the images will be generated if we move from this embedding to, let's say, this embedding. Okay, so if we use from this z vector to this z vector, then how the different images will be reconstructed by this variational autoencoder. So for that, we will call the same function which we have written here, this plot reconstructed. Okay, so this was to visualize the traversal in the latent space of the autoencoder, and this figure is going to be the visualization of the traversal in the latent space of the variational autoencoder. So you can see here that how these images are going on, and this is better than, right, 0 0 0, and then it gets blurry, and then you can see how the images of 0 are being shaping to 9, and how the images of 9 are being shaping to 7, and so on. How the images start with 0 and how they go to 9 and then to 7. So this is something interesting where you can see that in the latent space, it's a continuous distribution where as you traverse across those distribution and samples continuously, you can see a continuous transition from one image to another. Extra fun part is that what if we select, so right now we just selected 2 random vectors, right? Someone here, 1 point here, 1 point there, and we started plotting the images and see how these images are looking. As we are going from Z1 to Z2. The other fun experiment can be, let's get the Z embedding of one class, Z1 embedding of one class, and Z2 embedding of the sample of other class, and then try to do interpolate the Z between the Z1 and Z2 and visualize the corresponding reconstructed images. So what I mean here is, look here. This x1 is the image of 1. Okay. X2 is an image of 0. Given x1 and x2, find the latent embedding z1 and z2. Then once we have z1 and z2, we interpolate multiple sets between z1 and z2. So here n is 20, so we have interpolated 20 different sets between these z1 and z2. z1 is the latent embedding for class 1 example, z2 is the latent embedding for class 0 example. And once we have these sets, we give it to the decoder, visualize the reconstructed images and plot it. So you can see how this it is looking. It started with 1, it is ending at 0, definitely. This is what we expected. But in the middle, you can see a smooth transition from 1 to 8, and then 8 to 3, and then 3 to 5, and 5 to 0, and all of these images being valid and reasonably realistic. Similarly, if you try to interpolate autoencoder using the same embeddings 1 and 0, you can see that it was not so clearly able to model the transition from 8 to 5, which we could have seen here from 8 to 3 to 5, which is more realistic, right? 8, then 3, just remove a star and then just add a line there and remove a line, and then you have a 5 there. Okay, so this was a simple visualization of how the embeddings learned by this autoencoders actually help in reconstructing the images and what these images actually look like.